Oh, the light's flashing. All right. And there's the bar going across. We're live. Hey. Hi, I'm VertArbusto. This is the Schumann Resonance Harmonics channel on Facebook and on YouTube. Or YouTube and Facebook. Or mostly YouTube. Whatever. It's May something in Mediggy, the 13th. Oh, yay, lucky 13th. And it is Thursday. I think it's Thursday. Oh, it's Thursday. How that brought together. Okay, so what you're seeing up here, I'm getting right into this. What you're seeing up here, this is where I'm, okay, here. This is the CME, right here, this, assumedly. All right, now, you got to remember, first thing you ask is, what did it do to the ionosphere? Solar burst, okay. Between that and us is the ionosphere. Okay. So I'd like to remind people that it's like a balloon that expands and squishes, and there's a plasmic state that hard to explain. Outside of the balloon analogy, it's really difficult to explain the ionosphere. And a plasma is like a rubbery sort of substance that's not really a substance so much as a gas, but it can act like a liquid. It's very it's very difficult to explain, except if you think of sludge, right? It's part frozen, it's part water, it's part ice. Uh, I have been I've said this before. I've used the lava analogy, lava flowing, that once you heat up the rocks to a certain temperature, they start turning, they liquefy. Um, when you have soil that would normally be solid with both with water and with vibration, a resonance frequency, you can get it to liquefy. Uh, Quicksand has that sort of how do I say, a viscosity to it, because it's uh, part organic like peat moss, or like part sand and clay, and seeped in water, a boggy type of place. Um, so when we talk about current, we talk about the flow of water and the flow of electrons. It's a very similar kind of thing. And so because of the fluid elastic state of the ionosphere, the atmosphere above us, the different layers of thereof. And I'm going to just go do something really quick. All right. So this is the ionosphere. Okay. Hold, please. Hold, please. System processing. Please wait. Okay. Needed a picture to show you. So you see the various layers of the atmosphere. Atmosphere. Okay. And so the temperatures, they show you a temperature in Kelvin going upward. Okay. And then the various layers. So we're talking about, I'm the wrong one. All right. So they show you the temperature on the bottom, Kelvin. This is electron density in centimeters squared, and that goes up to 10 to the, I have no idea what that is, 4, 5, 6. I think that's, this is the various layers of the atmosphere. I'm going to do a course on the atmosphere and more in depth, but I wanted to show people here, while we're talking about, I keep consistently saying, what is the effect on the ionosphere? And that right there, this is your drum head. Okay. Now, why don't you dig on this? I'm going to take a hit of coffee. 5 minutes, good stop point. 5 minutes is a coffee break. Okay, good. Okay. All right. Let's go back to where we were at before. So just keep that in mind. It says relationship of the atmosphere and the ionosphere. When we talk about the words, I use the atmosphere to mean a general inclusive thing up to the atmosphere and not necessarily out to the magnetosphere. When I refer to the ionosphere, I generally include the magnetosphere as well, the immediate part around the the Earth. And then there is what they call the magnetopause, which is, as I understand it, that's the whole process of the bow shock in the front and the nexus point and all of that goes around us. So that would be what I would call the Earth's magnetic field, the magnetosphere, which also includes the ionosphere. Bang. Then there's a waveguide cavity of the lower atmosphere. Then there's the Earth's surface, the Earth ground. Okay, these are various components. They're broken up into the first part, the ionosphere, and the magnetosphere is the IMF. That's the interplanetary magnetic field. That's what I refer to as the upper DC current. The lower DC current is what I refer to as Earth ground. The AC circuit is in between those. That's the bouncing of the magnetics from the lightning discharge, which breaches the two poles. It's basically the pole of the battery. The Earth battery is capacitor, as a power source. There's these two poles that exchange. Generally, it goes from high charge up in the voltage up in the ionosphere down to the Earth ground, but it's also can be Earth positive going to a lesser state up in the atmosphere, the ionosphere somewhere. That counts as well. That happens as well. That counts, right? It's a discharge either way. And once it flashes that amplitude in the atmosphere, then it sends out the magnetics. It itself is electric, but it's on the magnetic side because it's radio waves. It's once the lightning flash is gone, it's now radio waves. It's no longer optical, it's now radio waves and travels pew on the magnetic side. And so then eventually that's that discharge from point A to B or B to A, whichever have you, is what causes the initiation of the Schumann resonances. So depending on what the ionosphere is doing, always in all cases, that is there then the the resultant is the Schumann resonances. Okay, so one needs to remember an important factor in this, that both the scale of the upper DC circuit, the magnetosphere ionosphere circling around us, that is as I said, that's the upper DC circuit. That's its one high voltage potential side there. Then the Earth ground is the other pole of the current, which is the magnetics. It's direction. Current is pure direction. So you figure north to south, east to west. That's your current, your direction of current, which is, obviously on the plane, Earth plane, Earth ground, Earth surface. All right. So as it discharges one, the Earth has its own inherent current. It is um, the same scale as the IMF, the interplanetary magnetic field, in nanoteslas. Okay, nanoteslas, which is like -9. The 0 point and then bunch of zeros, 9 zeros. The Schumann resonances come as a result of the discharge between the two. Okay, the Earth ground does not leach out its heart rate as such, people think. No, no, no. The earth keeps her heartbeat in her chest, moving along the rocks, the soil, the rocks, the ley lines, the telluric currents convey the earth's current within her. The Schumann resonances are a different circuit altogether as a result of a discharge between A and B. There's a whole different discussion people want to have of the Earth's rising vibrations. It will cause what it will cause to the Schumann resonances. And I'm like, oh, honey child, there's a whole world of discussion that you need to know and understand before I can answer that, because that's not an answerable question that I can answer, because there's a lot to that. So anyway, all right. Okay, so we're at 11 minutes now. All right, so this is technically not a short anymore. I haven't even gone into the material. I'm still working on my introduction. All right, so that's the two circuits. Again, I mean, it's important to, just remind us all what the Schumann resonances are and what this is doing and what it's picking up and how to read that, because this is how we're going into this, of having to understand the two antennas. Okay, there's two components. The first antenna, the dipole, the electric side, picks up a certain range. You have to remember, it's not dialed in to pick up X-rays and gammas and any of that. And so even if they did manage to come through the ionosphere, what they call the transparent layer, apparently, I just learned that recently, the transparency layer, all right, it gets through it. You still are stuck with the fact that, there's the first line, all right, it getting through the ionosphere is one thing, down into where the antenna is, right? The antenna isn't in outer space. They have a satellite that measures that. But no, the antenna, whatever happens, whatever light has to get to the antenna first and foremost. And it's not optical light that it's reading. These are radio waves picked up by an antenna. And as someone who's worked with antennas, that's how I got roped into this gig to start with, because I've worked with so many antennas and radios, and this is an extreme fascination. This is a fetish for me before I got into this, or a hobby, is that you match the antenna to the wavelength you're looking for. It's that simple. They have different size, different configurations of antennas based upon the signal that you're looking for. Okay, I had to clear my throat. I don't know where I was. All right, so let's see if I can do this gracefully here. Bam. All right, good. All right, good. All right, good. Hold on. Hold, please. Okay. We are at the wreckage of the tail end of the CMA. It was notable. It hit the KP of 7. I don't go over too much of the space weather stuff, because it's this Wages World does that. All right, he does a lot of that. I'm not going over what he's already done. In some cases, I couldn't do it any better. And a lot of you are from there anyway. Okay. Yeah, pretty much. So I'm operating under the kind of the adult side assumption here that you all know about the CME and a lot of the space weather. And so my part in this is not space weather. It's up to the ionosphere. Kind of the parameters of the Schumann resonances are from the ionosphere to the earth ground. Okay. Now I know what's happening beyond that, because I pay attention. I watch Wages. He does the groundwork for me, and so all right. So hey, now that this is the advanced class, he's giving you the basic, and I'm giving. All right. So now that you've already been to the other instructor, time for the Verde's Schumann resonance harmonics deal. And I really kind of like that, truth be told, the specialist in something, but especially in, Earth atmospheric electromagnetics, which are really cool in my opinion. All right, so like I think you should be able to see in the top, where am I? Okay, and so the top here, this is the website. I go to disclosurenews.it because, not that there's not other places. I mean, the other place would be the Tomsk website itself. I go there, compare them. Is this down? What are they doing? It's important. Uh, but it's because they show all four of these together. I'm happy to support them. I haven't given them money, but if I had money to donate, I donate money to them. They got somewhere on the site. Yeah, they got their, so they don't, on the main disclosurenews.it site, they have a place for donate and all of that. And so this is just a pop out for the Schumann resonance itself, which, and again, I'm grateful. So I'm glad to, support them. Disclosurenews.it, Wages World, goes to, at least he, gives a link there to him. All right. So I have given, oh, good golly. I, the job here has been to kind of help you read what are you seeing from the technical kind of level. And so that's why it's important to know not just what the spectrogram is saying, but also what the dependencies are reading as well, because that's where I'm getting my information. I've said this, I couldn't tell you what the spectrogram means, the Schumann. I can't tell you what the Schumann means without knowing what the rest of the class, Herr Schumann's class, said. His little dependencies, the 12 disciples. That's another way to look at it. That's Jesus. Is this your religion? This is Jesus up here, and these are the 12 disciples. All right, that's a great way to think of it. I think Jesus would be all for us learning this in the best, most expeditious manner we could, and the savior of your choice. Like, is it Schumann? Schumann wasn't a god, Jesus was. All right, so just think of it this way. Jesus needed his disciples. I need pictures to show people, and I try to have fun with this and not be disrespectful. So, if Jesus is your thing, I have great love for him as a prophet. We're all part God. Inside, we all have that divine spirit in us, and that's what Jesus said. I'm a regular guy. It's through my Father, so go to him. I'm not, greater than these shall you do. Greater things than these shall you do. All right. So the whole point of that way tangent was that this right here, this is our CME impact, we'll say. I'm only going to say that. Boom. Hits the ionosphere. You saw that, the little bump out curve there. All right. So ripples down, compresses down, ding, 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 lower layers. You got to remember, this is still lightning. Or somewhere in the line is a release of Earth's telluric funkiness function. So we have the Kumania sites that have the seismograph deal on that. It measures the seismograph. All right, the Earth's movement. We aren't privy to whether or not they're measuring the seismograph over there. However, there's not a seismograph meter here for us to know with that. All right. And that's not what the Schumann resonances are. That's not what they're set up to doing. The Kumiania is a lot higher in the amplitude for a different reason, because it's picking up different power source than only the atmosphere, and that's what these guys are doing. Only the atmosphere. It's not the ground related stuff. However, if there is electrics, and one needs to remember that the closer the lightning is, the higher the amplitude is going to be. All right. So that's why that's a tricky thing as well. That if you are near lightning strikes, it throws it way off. All right, so it's something to remember. Now, you could yeah, a lightning strike is just instantaneous. All right, fairly instantaneous. Okay. Um, However, the the globe around, there is a fair degree of lightning that does happen in the atmosphere. Um, and what is that? That is the discharge between, again, it is the discharge between the upper atmosphere, the ionosphere, and the earth ground. A lot of lightning is formed in clouds, but also if there is storms happening, like with hurricanes, hail, this type of things, a lot of times there's a lightning that's associated with that. Um, and so it needs to be remembered that it's not just even the local climate there at Tomsk that colors this, but it's also, worldwide. Is there tornadoes and hurricanes that are causing this, sending off lightning? It's atmospheric lightning. It's atmospheric uh, EMF, and it would subsequently need to be considered. So the point I'm making is that it's many people's first assumption when we're talking about the Schumann resonances, blipping, blurping, blopping, uh, you know, peaking, um, 6 hours of peaking in the middle of the day, 8 hours. What is this? 11 to, yeah, here, a normal thing, 11 to 9 at night, 10. All right. You know, so that's 12 hours there, 12 hours of sunshine. And then even at 5 in the morning, it starts as a little dip as the atmosphere readjusts. And then, bam, full on at 11. And then till like 8 at night. 8 or 9 at night, and then 10 occasionally, whatever. It's if it's still a party going on, right? That's Tom's normal cycle here. Okay, and then the middle of the night when it's all slackified and we're sleeping here, boom, boom, boom. There's still some resonances is going on, but there's not much in the middle of the night and then during the day. All right, so here at 11 it starts, 12 the middle of the day, 1 o'clock. Okay, and then there's not much activity. All right, but we look at it here, 12:20. Okay, hold please, system processing. I need to get into. I'm starting to get into. Let me build my book. All right. So, woo, I'm going blind. I'm going blind. I'm going blind. Can't you see? I'm going blind. All right. We're moving. We're grooving. All right. You kind of look at this as the numbers, right? Paint by numbers. Paint by numbers. Paint by numbers. All right. As I've talked about, all right, and I've given folks. I think I started saying this. I've given you different ways to look at this. Uh, from the purely technical and the engineering and all of that, the wonderful stuff, and how I think of radio antennas. And you got to remember, a radio antenna is measured to a certain size of radio wave that you're looking for. Radio wave frequency is measured in kilometers or meter or centimeter, whatever. There's a band, a centimeter band, millimeter band, a decimeter band, a picometer band. Um, and so when we're talking about X-rays and gamma rays, those are tiny, tiny waves, and those are not picked up by the Schumann antenna. Those source waves, those source, and they're not even waves at that point. They're like photon energy. It's a vector. It's not a wave because it doesn't have peaks. It's all in a plasma, straight on DC forward march current. That's how it's coming to us, and so that type of energy, the X-ray, the gamma, all of that is high photonic. You know, a lot of it gets caught up in the atmosphere, yes, but then it still comes down to us, and it still hits. But even then, still, it'll have an effect on you. But it's technically speaking, because of the way the antennas are tuned, it's not picking that up. And in addition to the fact that they're also filtering that high squeal out of the system. So it's kind of a 1-2 double jammy that you're dealing with in the direct reading of the antenna itself, as I believe people feel that happens, that I try to dissuade people from believing as a notion that it somehow contributes to these readings, because knowing what I know about radio and antenna, that, you know, what has to happen and how it's filtered, you know, I just need to give my technical experience and expertise on that point, those points of what the radio wave antenna of the Schumann detectors is actually picking up. Okay, so on that kind of disclaimer and that cheery note, all right. So this is our theoretical CMA. I'm happy to admit that's the hit we took on the ionosphere. It was not that big, right? I mean, relative to these things, and not as, you know, but it was brushing. We got tickled. I'll put it that way. This is a tickling right here, midday. All right, so we're looking at how to build up the colors. All right, so I mentioned this before. When we're looking at these peaks, all right, so it's 12, not 12. All right, so this number right here, 53, okay? Yesterday's peak was right there, 42.8, okay? That was yesterday's peak, and that's where all these guys are here, all right? Those are peaking at 48, or 42, rather. All right, so this is our peak right here. This is our where we end right here. This is 53. That mark right there is 53. And this is decibels. Decibels of electrovolts. Pico electrovolts. Okay. So we're looking at this from the baseline is 2. Our max is 53. So together that's 55. We divide that in half is what, 2750. All right. So that's our mean. I think that's the number. I think that's the name that's called. The mean is when it's in the middle. You do that kind of a quick addition. All right. That's our 50% mark. 50% saturation of color. Okay? That's what we're talking about, where you can start seeing the blend of color from one to the other, is that 50% mark. All right, just have to think of it that way. As you're looking at the colors and matching it up, how do you get the colors on the graph? Well, you paint by numbers, which are these right here, these numbers right here, okay? So this, if you think of this as a paintbrush and it's going vertical, making vertical stripes, okay. Your palette, this is your palette, the yellow, the red, the green, this is the palette that you're using. Okay, so the tippy top of the yellow color is 22, the bottom is 2. All right, so add together, that's 24. You divide it in half, that's 12. All right, so 12 is right about here. There, all right, so it's 12. All right, so it goes to, see, this is going to the top. All right, this signal is going to the top. And I've shown before, I've recently been showing you this, so you sort of have the color code of how to figure out what you're looking at, right? I think it's really important. I can sort of tell you, but I want you to sort of get some principles of what I use for principles of how to figure this out. And it would be fun to have people to talk to about this, to, you know, so you know we can kind of work in this together and build. You know, so every time you look at these, you have to look at, you know, I'm showing you how I do this, right? The 10, the 2 is 12, so half of that is 6. It's right about there. Right, so look at what's in the 6. All right, so this right here is your half point. So there's a few of these, red. So you expect red, and you look at this. Right, so that's lower. All right, so you'd expect to see a reddish orange color there. All right, and so look at this peak. All right, so then we're talking about a maroonish. The green and the red together is maroon. And a peak right there, 6.8. These are not big numbers here over on the side. All right. Remember, the green ones are the biggest waves. So 8.8. Well, that's an interesting. So 4.4. Where's that? 4. Halfway. All right. All right. So you see what's halfway. All right. You get maroon as a base of that, more maroon. And then this here. 12. All right, so that peaked just at the 50%, the saturation. Those are just at saturation. So the red, you'll see a little bit more red in the orange. And then, so that's what you're looking at there. See all this red and the orange in there? That's what we're looking at right there. The maroon, green. So when you're looking at these, we're doing the reading. To do a proper reading on this, you know, what is the white? The white is the white mode of this. And the how do I say it? The strength of the white mode, the intensity, the apparent intensity, the apparent intensity that you're seeing on the spectrogram of the white mode is the white is the tallest of the waves. Okay, this is all based mathematically on a ideal wave. Mathematical is a formula involved of how they get the mode, the shape of the modes. So, and I've done a show on that. I've done videos. I've talked about that. The modes, but the modes are basically the size and the shape of the electric side in comparison with the magnetic side. Okay, so that's part of what it is. It's a mathematical shape in comparison, in relationship between the height and the width of it. Okay, because remember, with an electric, you know, it's electromagnetics. With the electric, the voltage, also comes the magnetics, which is the amperes. Okay. Amps. Okay. So, so when we're looking at why or how, you know, we're getting the colors, you have to look at the supporting percentages behind it. If the yellow is not very tall, and we've seen they can vary from, you know, from size to size, you know, it's just a theoretical shape or theoretical model that these guys fit in. So if there's more of a lower, you have to remember there is in theory an equal amount or a proportional amount of electric to the magnetic. So there's a mathematical average, a mathematical formula that it's looking at based on some, you know, the strength of the signal at a certain range. All right, just trying to keep it general and still not sound like an idiot explaining this. And so that's one of the things I talk about, synchronous mode, when the wave form is fairly identical across all 4 modes. The different, you know, that means it's solid. It's a solid wave coming from the upper ionosphere. Okay. A more pure signal. That's how they kind of look at it. So the quality, when we start talking about quality, it's the degradation into magnetics. Okay. So I make it up. You can see the amplitude. It's a big thing. Everyone wants to know about the amplitude. Okay, all right, there you go. All right, so that's how you read that. That's the uprights there. And you have to remember at the same time, there's a different antenna. That's why it looks the way it does. It could, the spectrogram could look a different way if there was indeed one antenna that measured it, but they don't, there, you cannot have just one antenna. The spectrogram doesn't read, it doesn't read the data as properly as it actually is in real life. I think that may be the best way to put it. It's a representation. That's why people get all, why I try not to stress too much when people go all crazy reading the Schumann, because they don't know what they're reading, and it's a representation, and then there's some issues of how it's plotted, and I know technically this because I know what it's doing, so there should be more of a weaving, an obvious wefting and weaving, and there isn't, because it's the amplitude outshines the other signals. And that's the problem with that you should be seeing. See, it's all one there, and it's misleading to people. They call it a whiteout, and it's not a whiteout. It's just the way it plotted the data there, my dear. You know, because you can see these strong signals. A tall number, a big number here, would be 8.1, I think. So you can see this is getting pretty high, all right? And these down here can be, this can be a lot more. This could be 30. So the green here, this is not that high relative to, yeah, but you see the frequency of it's getting kind of high. The frequency can get up to 30, okay? And this this is the pico Teslas here. This can get a higher reading, so it's not that high. But you look at the numbers here, the combination of numbers. So, you know, for those of you who are into the numbers, numerology stuff, you got to kind of look at the number here, 1330. Well, I'll be dipped, all right? Right there. It didn't reach the peak of that. Hit that yesterday. What is it? 1330 at 2 and 4. 3. No, 3. The 2 and then 3. So it hit 1330 at 3. Right? So there's a peak here, 17. All right, so we're at the magnetics, we're at the quality. I have more fun talking about the quality. The quality is what causes the Schumann resonances, all right? Just that simple. The amplitude is like hitting the bell, but the magnetics going around the world and bumping into each other eventually is what causes the Schumann resonances. And that is the more important part of it because it's the more lasting effect. You know, the amplitude comes in, strikes, quick, all right? And remember, you see those amplitude spikes in the middle of the day. Remember that. I keep pointing this out. From 5 in the morning till, 9, 10 at night, that's basically the day at Tomsk. Okay? And then you can see it goes to sleep. Mention that. You've seen it. You can see it. So this is a really important thing to remember. The magnetics are what you're stuck with. The lightning is fairly quick. It's instantaneous. We're not, you don't need much lightning for it to show up on the Schumann resonances if there's not much else going on, right? But there may be storms and stuff that are happening that actually are adding to it or that are taking away from it in some way, because the Schumann resonances, remember, are the electromagnetics of the lightning discharge or maybe some other stuff, but the solar gets caught up in the ionosphere first and foremost, okay? And the Schumann antenna is not an optical light reader. So this was not white light, gamma, 5D, anything coming in, ever. That's not what the Schumann antennas are measuring. So when you're looking at the colors, okay, you're matching up, like here, like this 22. This is a full all the way to the peak. That's 100% saturation. These all hit 100% saturation. And once again, when we see in pretty much all cases where there's the white, there's also fringed with the orange. You have to remember to look at this, fringed with the orange and the maroon, uh, the peach color, and then the green, the various green, the aqua, the teal. That's when people, generally speaking, most people, a lot of people, they look at this, they just want to look at the thing here. They don't see spikes. Oh, I'll feel okay today, right? This is the common, people's common understanding of this. They come in, they look at this, they see a little spike here midday. Oh, okay, that's good. There's nothing happening. And meanwhile, da 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 dum, there is something happening, and da 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 dum, there is something happening. This is 8. That's a high number. Frequency, this is kilometers. This is 8,000, unless I'm mistaken. I've had to piece a lot of stuff together. I've guessed some stuff. So unless I know otherwise, if you got proof that proves otherwise, great, let me know. But as far as I know, this is 8,000 kilometers. Okay, so this is peak to peak. This is measuring peak to peak to peak. And as it dips, ba-dang, dang, dang, you're going down to 7.35. All right, so the frequency here that you're looking at is not the harmonics frequency. This is the frequency in kilometers. This is the kilometer. This is the size from peak to peak of the waves. This is how they measure radio waves. And I know this because I've worked with radio, and I know how they do radio, and I have a radio to show you. That's what kilometer, that's what AM is. That's what FM radio is. AM radio is amplitude modulation, that's the height. FM is frequency modulation, that's the speed of it, which is the wave peak, going quicker. All right, so one of the things that we're looking at here, and I have this set up, so I'm just showing you the spectrogram. This is the money shot. This is the meat and potatoes right here of what makes my report so much different, that I give you the numbers and all of the technical stuff of how to actually read this from the standard engineering point of radio. And I try to do it in a simple, non-confusing, high school level, vocabulary as I can. But on your part, there is some reading required and some background required, and some background education required to start learning some of the vocabulary. It's a job. It's, if you want to learn this properly, this is complicated stuff. It's not for everyone. I'd like to say that oh geez, if you put your mind to it, you can get it. But hold on, I got to proselytize here for a second. All right, look, I need to tell you this. I was born to do this. I'm mutant, crazy smart. This I've posted before. I have a crazy, stupid IQ that should be put to better use than this. I humbly submit. And I would like to say that anyone, John Q. Public, if you put your mind to it, you can learn this. I would like to say that. I wish I could say that. But that's not true. I can't lie to you and say, well, if you just apply yourself, you'll get it. I have 30 plus years of radio and audio and video and meter reading and all of this stuff. I paid attention in high school, and I was in engineering classes in college, and I worked with meters. I am a hands-on guy. I know how to build antennas. I know how to. I do stuff. I was doing stuff before this, in this field, and so I'm giving you from my understanding of the practical knowledge of how all this works. Feel free to get whatever technician you want to read the meters for you. That's fine. It's free will. I don't care. I'm not making any money on this. I don't care. So, well, except for Bonnie, thank you. It's not really making money. It's just investing in more stuff for the studio, more toys for the studio. Bonnie and Jackie and David Julie, from Patreon. So those are the people and Susan. All right, so those are the people who've given me money. Thank you. And Wages, he hasn't given me money, but he's sent people over to me. Thank you. Much love. All right, so You know, what's different is I try to give you what the numbers mean in addition to the Schumann resonance, and why I am really particular about calling it the spectrogram instead of the Schumann. First, because calling it the Schumann bugs me. You've deified the damn thing. Okay, all right, fine. It's the Schumann resonances. Uh, um, but more importantly, calling it the spectrogram indicates you understand that there are dependencies to it that make up the coloring behind it. It's not, the spectrogram is not graphing the environment like people think. I don't know how to put it any other way to say it is hollow. It is just empty. Watching most people's pretty much everyone else's reading of the Schumann resonance spectrogram. There's few that are better than others. I'm not mentioning names and all in any way. Um, but publicly out there in YouTube land, it's disheartening. Um, Best do their best, people do their best, but people need to do more reading. But this is the problem. The best is still I have a lot of practical experience in this. And this is my issue of why it was told that it's important for me to do these readings, because for me it's a snap. It's easy. No one else gives you the dependencies and then tells you and shows you. They don't know, they have no idea that the spectrum, many of them have no idea there's even the spectrum that they're connected in some way. You're like, if you watch Bob Ross, he told you what he was doing as he was, and then he had like instructional books and videos, and like, hey, you can figure it out too, but I don't know. This seems a little bit more difficult than that, I think. It's not to me, but I have a good amount of years behind me, you know, taking apart radios, going to tech and learning electronics. I've taken networking computer courses. I'm a hardware guy. I've fixed computers. I've pulled them apart, put them back together. I still have one I'm still trying to work on for one of the YouTubers. It's just the software has moved faster than the hardware. Oh my God. Anyway, um, I'm a tech guy. I've shown you pictures of the studio. I do this stuff, So for me, it's a snap, and it's in service to my contract to do this. That I'm here. And if I can get some donations, that's great. It's icing on the cake. Please get PayPal. Like, it's a thing. I put my, somewhere I have the PayPal thing. I appreciate the donations, but that's not why I'm doing it. Not even doing it for the thank yous. Otherwise I'd have been gone by now. Um, but the people have learned. There's, the terrific 10 are the people who have learned something. Uh, that from what I've done, and they've mentioned it. Like, that's what makes them terrific, right? They've learned, not only have they learned something, but they've let me know what they've learned. And when I do a live stream, and I'll probably do this as a premiere, I think. A simple reading. This was going to be a simple reading. Um, uh, good thing I didn't. Good thing I didn't say quick. I try not to say quick because I know better. I try to set a time limit. I've mentioned this. Try to set a time limit. My time limit for this was 33 minutes. Yeah, so that's come and gone. So at this point, my next time limit is an hour. Like, okay, that's creeping up quickly. All right. So just all right. So with all that having been mentioned, um, we're we're looking at again. I've talked about diurnal patterns. This is one of the things I want to point out. The frequency is dipping as we see a peak a lot of times. The frequency of this is related to the quality. You got to remember that, because the quality is the magnetic waves that are traveling around. After the lightning flashes, it travels around. And then you see there's a dip in quality. I mean, a dip in the frequency a lot of times. I've noticed that. It's not, there's over and above the diurnal, there's generally speaking a nice kind of even curve to this. But then you see sometimes it just will drop like that. You know, they're okay. But then it goes to a pretty serious dip. All right. That's a notable dip. Okay. But then there's a peak here, peak here. So these are just things I've noticed. I'm not, I'm still kind of piecing it together, but there's a definitely a relationship between the amplitude flashes and then a dip in the frequency as it adjusts, and then it kind of picks up again. Okay? So, and there's an inverse relationship between the uprights of the amplitude and the horizontal of the magnetics. That the field generally is related between the two, and so you would expect to see in mode one. I've talked about this before. You'd expect to see in mode one a relationship between, normally speaking, for lightning, that you'd expect to see a peak in amplitude and then a response in the white mode. So you see it kind of drops down and then it picks up again. Okay. And so this is one of the things I look at. I compare the mode, the white mode to white mode here across the board, because that's what we're looking at. The coloring. So the white, where are we seeing the white on here? Okay, see the white in the upright. Okay. Now, got to remember that white on the chart, if it's not the amplitude and peaking, because again, with the white mode, a lot of times there's a yellow backing it. So that's why you have to remember that coloring combination throws it off. Okay? The white and the yellow together are, it's white. It's going to kind of blind everything else. Like if you're looking directly in the sun, I don't know. The machine, like, get blinded by that. I don't know. That may not be the best way to look at it. Like, I don't know. I'm trying to give you pictures, analogies. May not be working. That may not be the best analogy. But that's kind of what these whiteout conditions are. You see the yellow is right behind them, and then there's an orange, then a green, right? And so by the time it gets down to this wave size, right, it starts like that, and then as it moves down, it goes like that. So it's part of what it is this is kind of the bottom of the wave, biggest part of the wave down here, or down here. Here we go. And it's going to measure a different height than the height of this. Look at this. The height of that is 68. You have to look at this as like the height, literally, in feet, if you will. Does that make more sense even to you, I think, to people? If this was the height of this wave was 6 feet, if you looked at that, instead of it being decibels, it was 6 feet, or 60 feet or 600 feet. Then this is 2,200 feet, and this is 5,300 feet or kilometers high. If you could picture it that way, you'd say, oh, I see what you're talking about. And so that 53 kilometers height has to be fit into 8 inches. Right? So it's scaled to fit. All right. So I just want you to think of it that way. I like giving you geometry. I like giving you physical kind of ways that you can think of this and figure this out. I've given lots of different types of ways, and then, like, I'm not sure if some of them contradict each other or walk all over each other, whatever. But I think it's more than just, because I don't, even if I knew how to explain the equations that they throw out, it wouldn't even matter, right? I think it's not anything, right? I think it's important for you to get an everyday sense of what it is, what's happening, and how to read the colors technically Like from what I do, how I read it, right? This is what I'm looking at when I read one of these. I look at the size and the shape of the wave all together. They're all nested in there. Oh, okay, all right. And then what's the effect? All of that together, pound for pound, which one matches up? How do they match up? White for white, yellow to yellow, red to red. All right. And then the coloring. You start seeing the middle grade in here of these two together, the yellow and the red or orange, and you always see the orange around here, and then you see the orange is floating around, right? Well, that's these two here, the red and the orange. And then sometimes you'll see some maroon as well, darker orange, comes to reddish. You see these little kind of blood red splotches in here. All right, that's what we're looking at. Yellow, red, orange. There's not much white because the white's taken up. It's not a strong enough signal down here. These are bigger, right? See this? With the quality that as we start moving down, like these numbers are taller or they're fatter. Technically, not taller, they're fatter. Right? So that's one of the things. That's why the white, you don't get white here usually. You don't get white running across this way. These are the horizontals. This is magnetics. Remember that. The horizontals are the magnetics. And so you don't get much white running this way, like I said, because it's a narrow width. And as you start moving to the yellow and the red, and they're fatter width of the signal. And so they're going to kind of what's the word? They're going to overpower the white signal, the white mode. Hopefully that makes sense. I think it makes sense. It makes sense coming out of my head. There's a another way to put it is there's the geometry to this, that you have a upright, and then you have, I've described the flagpole as the fulcrum of the seesaw. I think that's a great analogy when we're looking at this, that real life is going out in 4 dimensions. There's a time factor, time variant, left height, length, height, width, and a time variant, 4 dimensions. Okay. Varying time dimensions because of the amplitude moves at a different frequency, different speed. The amplitude moves at a different speed than the frequency of the waves. Okay. We're measuring height, width, and the distance between them. And so each one of these is a different time scale. Okay. Frequency, each one of these is a different time band, time designation. 7.3 to 8.4, and this time variant is 12.7 to 14.8. Then you have 18.5 to 20.80. Then you have 24 to 25.6. These are different time variants as well. So there's another 4th dimension that's floating around here nebulously that we are trying to factor in there. So we have 4-dimensional waves, the light, all of this, 5D, whatever. Make it more complicated if you want. I'm gonna leave the 5D out of it. We're just 4D, Newtonian physics. We'll just keep it to Newtonian instead of quantum. Okay, please. All right. This is bad enough as it is. So you have it moving in like the hand kind of thing, moving in and out like that, or like that. I guess it says that the current is moving. Well, technically, the current's moving through it that way. You have a wrap around like that, and a wire. Okay. In the air, it moves out in all directions, up. Yeah, that's me gesticulating in the studio, almost knocking my mic over. Um, and so you have it moving in all directions, up, down, across, all of this kind of stuff. So one of the things that we need to remember is that we can only plot in 2 dimensions. It's a flat doohickey. So you're trying to record four dimensions, essentially. The time, you got time variance in there, right? As well as length, height, width, blah, blah, blah. So sending it out. So it's extremely difficult to do that, to picture that in this form. So when I give you the analogy of the lightning pole as the amplitude and the seesaw as the magnetics, that gives you a good way to kind of keep it flat. Right? And then if you were to push the flagpole and the seesaw just in a straight line, like a car was pulling that, like it's on a trailer or something. I don't know. Right? Picture that. But the flagpole and the trailer, it's mobile. You can do that. All right. It's not anchored into the ground. So in our example, a rolling example of the 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 geometry of the waves, you have the amplitude of the flagpole and then the seesaw moving with it. Right? That's how you're picturing this moving across. And what we're looking at is the density of the blue in the background. Okay. The dark blue, I've talked about this before, but the dark blue is the at-rest state. This is our theoretical at-rest, numerical, statistical at-rest state. But there's not much going down here in the lower frequencies here, not here, but over here you can see some stuff going on. All right, and especially, here in the lowest. These are 1, 2, 3, 4 hertz. 4 hertz. This is below a lot of activity below the fundamental harmonic of 7.8. Okay. So we have kind of this void here and this kind of atmosphere. There's not much going on. Okay, generally speaking. All right. So this is our harmonic frequency here going this way. Okay, these are harmonic frequencies going that way. And so you got to remember that it's against the blue of the background. Okay. So that blue is ever present when we're doing this, when we're looking at this, when we're kind of figuring out the color scheme of this. There's always something going on in the Schumann. Okay. The Schumann and his dependencies. I might do a little, comic clip of the Schumann and his dependencies, like Jesus and his 12 disciples. I'm digging on this, I think. People turn it into a religion. I'll make money on it, tax-free. I'm good. I am a prophet and a priest of the Schumann religion. There's money in it. Okay. All right, fine. It's only it's only a real religion if it's tax-free. Okay, on that cherry note, it's actually time. I should probably wrap it up because it is time. My target was an hour right now. All right. All right, there's still more to talk about. Uh, so when we're looking at these aqua, teal, kind of color, turquoise, aqua, teal, the blue, a variant of the blue-green, that's because we have a activity of either a green or a white. So the green against the blue will give you a teal color, and the white against the background will give you like a light blue color. So the difference of that is the direction it's coming in. So the white, if it's like a blue, baby robin's egg blue or light blue, that would be coming from the white end of the color, white end of our palette. I'm just going to call the dependencies the palette, right? And as I'm going to be doing more of these, I really want to help you develop how to read the colors properly, because there's a lot of bull crap out there of what the colors mean. And oh honey, oh just no. Whenever on the Facebook, whenever I see those postings of what the others give you for what the colors mean, I delete it, and I may delete the person, the author that posted it. No, I don't want any of that crap around, because it's not even close to what it is. You have no idea what you're talking about. You're only basing it's a witchcraft, voodoo. If you're basing your hyperbole of what you're seeing there only on that and not the dependencies, you're not bringing the dependencies into it, the disciples into the picture, you're a shill. You're a troll, right? It's not science. Right? You're not giving a technical explanation. It's fine. You can do whatever on your channel, but that's not what this is. What people are bringing into this. So from my perspective, I'm giving you technically how to read the radio readings from a radio antenna. Okay. All right. So there's more that I can go to, but I think I've said a lot. This is definitely a longer video than I'd intended. Good thing I didn't say short. All right. Yeah. So I'm not quite over. Right. Oh, where's the other one? What do I want to? So this is the CME, right? They're talking about basically. I just want to show you. Yeah, see there. All right. So see this going. All right. Okay. All right. So we just got the little edge of it right there. I knew we'd get something. I knew we'd get something. The model they predicted, I had thought it would be the backwash of it, the backlash of it. I knew I knew it was going to miss us. And even if it doesn't, it's still going to hit Mercury. I know it's hitting Mercury. I know it's hitting Venus. It's hitting Mars. The whole solar system is changing. It's just changing. It's time. It's the wrap up. This is the wrap up of the wrap up. Just get your affairs in order. Do well, be well. Like I'm smiling. I have a oh yeah. I have a message of hope and faith. Not that things are going to get better. No, that's not happening. Everything's breaking down. But don't lose your vision. Don't lose trust and belief. And just stick to what your guides tell you. And know that there's a bigger plan and that if you don't lose hope, you'll be part of the bigger plan. Right? There's a lot of people running around like crazy. You do not have to be one of those. Ground your energies, no matter what is happening. No matter what is happening here, all right? You are the center of your universe. You need to ground. Just don't ever forget that. It's not the problem of the Schumann, whatever the Schumann's doing. No, if there's more energy that's out, you need to do more grounding in order to get rid of it, to disperse it. I took on this obligation to talk about atmospheric electromagnetics, not just the Schumann. There's other electromagnetics. And so I always make a point of mentioning that regardless of whatever the Schumann is doing, if you have unshielded electromagnetics, you have fluorescence, you work in an office where you're being poisoned by the plastics, you are in your car a lot where you're being poisoned by the plastics in there. Um, time to reconsider. I humbly submit to you. The reason people don't want to go back to work is they are tired of being poisoned by the workplace and by managers who are just DBs. And by DB, I don't mean decibel. By people who just are not very nice. And by the jerk-offs who've been shitheads to get ahead, right? Those are the people who run business. No wonder people don't want to go back to work. No, it's not you. You don't want a handout. You want a job where I want a job where I can be respected for offering something and be rewarded if I've saved the company money instead of, oh, thanks. Or yeah, no, it's not because we want a handout. No, 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 honey child. No. People don't want to work because your working system's broken. That's why. It's just that simple. It is just that fucking simple. Your working system, what you have, we get you good. No, it's here. It's going. It's going. The shit that shouldn't have been together in the first place, it's going. All right. Okay. So, on that cheery note, it really is time to go. My proselytize session is over. Okay. So, where am I? All right. So, on that cheery note, am I? Am I? I don't know. Okay. All right. Whatever. All right. This is one of me anyway. All right. So on that cheery note, everyone have a good rest of your night. I am gonna make this as a premiere, and as soon as I get everything together, I'll post it. And everyone have a great rest of your night. Thank you all for being here. It's a lot of fun doing this. Thank you, Bradley, Jackie, Julie, David, Arizona Raven, Wages, as always, Mimi, um, Rogue Rebel, and some others. I can't name everyone, but that's just those of you who've recently posted, and it's much love to you all. And so, thank you all for coming, and have a great rest of your day. Namaste.